So in the keynote so far, we've heard quite a lot of architecture, but we've also learned that one of the biggest challenges facing us at our community in the adoption of programmable computing is how to program these beasts. And this has attracted a lot of attention of people looking at techniques based on C and other languages go to hardware. So it gives me great pleasure to introduce Deshanand Singh from Altera. And he's worked for a long time on programmable productivity tools. He did his PhD at the University of Toronto with 50 patents and papers, so he's well qualified to tackle this problem. And in particular, he's been focused on trying to take OpenCL and try and convert that into circuits rather than code for running on GPUs. So, Deshanand, please take it away.
Basically, FPGAs are becoming larger, more complex, integrating more IP, and arguably becoming more and more difficult to design for using traditional techniques. So before we get into that, I think it's kind of instructive to learn how we got here. If we look about 10 to 15 years ago, the spectrum of programmable devices, it was actually pretty sparse. Now, on the left-hand side of that spectrum, we had things like processors and DSPs. And these were programmable devices, they're just software programmable. On the far right of that spectrum, we had the FPGA, this massive, fine-grained array of logic elements. Programmable also, but programmable through hardware circuits. So let's look at what happened to the left-hand side of that spectrum. The sequential microprocessor, after about 40 years of unparalleled success, where performance just kept steadily going up and up, we have gotten to a point where we are getting diminishing returns now. Now, what happened with the sequential processor is that a programmer would express their algorithm as a sequence of instructions, a sequential sequence of instructions. They would operate on a conceptually flat data space. They wouldn't have to worry about memory hierarchy or where their data is located. But behind the scenes, the price of this abstraction was actually very, very high. The processor was doing a lot of very fancy things. It was dispatching instructions in terms of functional units. It was doing very complex dependence checking. It was trying to bring the data closer to where the computation was happening by having large cache structures. Now, all this circuitry, if you really look at it, is pretty large, pretty power hungry, and very inefficient. And for some of the reasons that Steve touched on yesterday, it's becoming more and more difficult to scale this kind of architecture. And it's actually led to a profound change in the space of these programmable devices. What we're seeing is that the spectrum is now filling in. In the middle there, you're seeing multi-core devices, multi-core CPUs. They're becoming commonplace today. So our desktops may have 4, 6, 8 cores, very common. You're seeing the emergence of the graphics processor unit, the GPU, where you have hundreds or even 1,000 very small floating point cores that are highly optimized for data parallel computation. And it's becoming more than just graphics now. It's becoming used for general purpose computation as well. NVIDIA is making huge strides in that area. Now, if we look at that middle end of the spectrum, just take a step back. What do these processors all look like? At a very high level, you can kind of think of it like the picture on the slide. The processors tightly connected with memory. They're arranged in some kind of array, communicate with each other through some on-chip network or maybe some kind of shared external memory. But the things that we're seeing more and more commonly with these architectures are that you're getting more and more transistors. The fabric speed is not really scaling, and Steve touched on that yesterday. So what do we have to do? We have to go to more and more parallel implementations to get performance speed up. So all of these architectures are becoming more and more parallel. They're devoting more and more of the transistors to actually do computation rather than the magic behind the scenes, such as the caching and the very complex IP extraction. There's a price for this, though. Programmers can no longer just rely on sequential C code to get the best performance from your application. They have to start coding their applications in a more parallel fashion, or at least making the parallelism apparent to the compiler so the compiler can do it for them. Now, if you look at various different spectrums of application domains, you'll see these multi-core processors everywhere. Now, on the top of that traditional packet processing applications. So this is a space where FPGAs really play a lot. So these processors are used for basically handling packets in parallel, doing all kinds of different operations on packets. On the bottom, you'll see different application domains there. Companies like Adaptiva, which use multi-core processors and low-power mobile applications. Telera, which has some very interesting applications in the video broadcast and networking space. And of course, NVIDIA in the world of high-performance computation. Now, I've kind of taken these first few minutes to ramble on about the wonders of multi-core, and you might be wondering what does this have to do with FPGAs at all. Now, last year at FPGA 2011, I participated in a panel where people were wondering the same thing. Where do FPGAs fit into this new world where almost everything seems to be converging on a multi-core solution? And this is a slide I took from the NVIDIA presentation that Mike Butts presented. And he showed what is significant of the FPGA is. And basically, you can see it here. What the FPGA is doing is basically taking data from sensors, doing some kind of protocol conversion, and sending that data over PCI Express to a GPU, and the GPU can then do the algorithm processing. So in his world, the FPGA has been reduced to a very fancy wire. All it's doing is some kind of protocol conversion using some very rich I/O structures. To me, this is a very, very great feature for FPGAs. I think we can do so much more with this. So, why? Why do I think that? So, let's look at a motivated case study. I like to look at this very, very simple example, just what we can do as an FPGA. Now, let's take this FIR filter. It's a very, very simple algorithm used in a lot of signal processing, image processing, many structures look very much like this FIR filter. Basically doing a combination of a filter with a signal. And if you take this FIR filter and look at the equations that you actually come up with when you're computing the outputs, what you'll see is that each one of the outputs on every clock cycle basically is completely independent. You can think of it as parallel threads. Now, I just want you to keep that in the back of your mind, and I'll come back to that later when I talk about OpenCL and parallel threading. But for now, if we take this FIR filter and the best possible implementation, a CPU, a GPU, and an FPGA. Let's assume here that the CPU, GPU, and FPGA are all the same process, use the same area. So I've picked it so they actually have all the same characteristics in this particular study. When we look at the absolute performance, now the FPGA absolutely dominates in terms of absolute performance in comparison to CPU, GPU, and in the CPU, GPU, and FPGA study. And what I'm doing here is sweeping the number of taps of the filter as we go along the x-axis. If we look at power comparisons, CPUs and GPUs, this particular study we're using about 70 to 80 watts. The FPGA always using less than 2 watts. So these are pretty low cost and low power factors. Now, of course, because our performance was so good, and our power was so good, our performance to power ratios are excellent. You can't even see the other two guys on this particular image. Now, these are the metrics that people really care about today. Performance, power, performance to power ratio. FPGAs absolutely dominate on this kind of application. Having said this, this is the kind of application FPGAs do really well. This is our record. Now, I started thinking, why can't we use the same kind of technique to express more general algorithms? I mean, the FIR filter, if you really look at it, has some of the same characteristics that more general algorithms have. You have a feed-forward pipeline kind of structure. You're using a lot of storage locality, where we can use the FPGA's registers and small programmers to do that very, very efficiently. And why can't we use the same kinds of techniques to get immense amounts of acceleration on other generation algorithms? Now, a bunch of people have done surveys of folks in the world of computation, high-performance computation. So this is a survey result from Intersect 360. And they asked both users and vendors in the world of high-performance computation, what technology will transform the world of computation in the next few years? FPGAs have 3 years of life in a standard system component for the last 10 years that will be so for the next 10 years as well. So tremendous skepticism about FPGAs in this world. So why is that? Well, why can't we bridge this gap? It seems that we're so close, but yet so far. So I'd like to look at our competition here for a sec to try to answer some of these questions. And the competition that I want to look at is the CPU and GPU, specifically the GPU. Now, CPUs and GPUs are used together in heterogeneous systems. And what happens here is that most of your coarse-grained sequential part of your algorithm will run on the CPU, your highly parallel part of your algorithm will run on the GPU. GPUs are programmed primarily with CUDA or OpenCL, very, very similar languages. But the big idea here is that you have a serial part of your application. It gets loaded into the CPU. You have somewhere specifying a parallel part of your application, and then FPGAs to communicate between the two. But for all the computational horsepower of the GPU, it's known that they just take tremendous amounts of power. I mean, high-end GPU cards may take in excess of 250 watts. The GPU that I have on my desktop, right, I require a separate instance of 5 watts. And if you look at how these things are used, any real practical application where people are doing lots and lots of compute is likely going to be in the data center. And the kinds of applications that we're focusing on here are in 2 domains. High performance technical computing, so that would be your scientific computing, your bioinformatics, your molecular dynamics, field simulations, things of that nature. And of course, high performance business computations, so these are financial computations, risk management, various kinds of analytics. And if you look at this whole domain, it's high performance computing, and it's almost 20% of the entire server market. Now, in these data centers, power and cooling is really become a top concern. Energy prices are hovering at near historic levels. Processor design is coming up against the power limits, so very high as well. And companies themselves are increasingly sensitive about reducing their carbon footprint. That's this level of so-called green movement. If you look at one of these centers, they average about 226,000 square feet. And the actual power cost that they're using is $3 million per year. That's just about 25% of their budget. And that's not their only cost as well, because at some point in the data center, you get to the point where you want to add more computation because it's key to your business, which you just can't. You don't have the power and cooling available to bring or to add more compute into the data center. So you have to upgrade your infrastructure. And if you look at the cost of upgrading infrastructure, it's about $7 million a year. So it's significant when you think about the impact that power has on in this whole data center world. Now, this is interesting because GPUs have these massive power requirements, but yet we see power and cooling as being one of the key data center drivers. However, GPUs are also not serving seen as having really bright features. And really, it doesn't add up to me. It seems that FPGAs are good at computing kind of these massive devices that we're not creating. We can do tremendous amount of compute. So why can't we just get them down a little bit and small? So I try to answer that. There are a bunch of challenges in terms of using FPGAs in this domain. The same group that looked at the future of HPC and what technologies will dominate asked the users or vendors again, what are the current problems in HPC? What are the biggest obstacles? And by and large, what they said it was parallel programming models and parallel tools as well. So, parallel programming models and parallel tools. The other thing that they highlighted was external memory bandwidth. But let's look at parallel programming models and tools to start off with. When a person has an idea and wants to create a new implementation, they usually go through this process. Get an idea, code up some C for it, go through a compiler, create a binary, they can immediately execute it on the device. And they can do very, very fast iterations. If you have a bug, you can easily figure out where it is, fix it. If you want more performance, you can use emerging parallel APIs like OpenMP, OpenCL, things of that nature. Compilation times are very fast. You get very, very fast feedback. This is very, very different than FPGA design. When you start from an algorithm, you want to make something from an FPGA, what you'll do is make a state machine and make a data path. Sometimes you'll have to replicate the state machine and data path. But this is just about your computation. You still have to connect it to something. So you usually have to connect it to some kind of object bus. If you want to actually communicate that result somewhere, maybe you have to send it over PCI Express to some post-processing. You have to have the data somewhere, so you have to instantiate DDR controllers and PHYs. All of these things are running on different clock frequencies. The interfacing to them is extremely complex, especially if you want to use them efficiently. This is one of the biggest challenges in FPGA design. All that stuff on the right, the interfaces are extremely difficult to design efficiently. So that's one of the key problems of FPGA design. Everything is done using hardware description languages such as VHDL or Verilog. That means you're specifying the cycle-by-cycle behavior of every single register in your circuit, and have to go into incredible amounts of detail, buffering, arbitration, IP core interface, all of these are very, very detailed things before you can even get your first working version done. Our CAD flow is also extremely complex. You have to go through synthesis, technology mapping, clustering, placement, routing. All of these things offer a tremendous amount of automation to the designer, and we're using very, very sophisticated algorithms and also taking advantage of multi-core devices as well. However, the compile times for our large circuits can range from hours to even a day, even with all of these optimizations. So it's very, very different in the software world. And it's not just a single compile, because you may have to do this in a cycle. You take your design, you run it through a vendor's CAD tool, you find out that you have a timing violation, maybe in your DDR interface, you do some kind of manual placement, maybe constrain it somehow, run it through again. Okay, you have no timing violations. Now you can run the design on the board. You find that you have a functional error. You have to go through the cycle many, many times. And that takes a considerable amount of time. Designs are also not scalable, because once you get a design that you're happy with today, and it's all coded in RTL, the FPGA vendor comes out with a device that's twice as big, and you want your design to go twice as fast. Now, just simply replicating your design is pretty easy in HDL. You can replicate data paths pretty easily. However, you can't just do that with all of your state machine and control logic, because you may have to add some pipelining. You may have to change how the arbitration works. All of those things are quite difficult in HDL and quite difficult to verify as well. Portability is also a huge issue. If you have VHDL, Verilog, interconnect, this is your grab bag of your design database, and you want to see how does this run on a GPU or a multi-core CPU. Extremely difficult to do. There's no tools to allow you to do that automatically. So it's really a big fundamental drawback of FPGAs. This is what's limiting us in this world. Generally, software programmers won't accept all of these drawbacks. What we need is a programming model that allows the designer, the programmer, to think about an FPGA as if it were one of these multi-core devices. And the ideal programming model would probably have these characteristics. It would be based on a standard multi-core programming model, which is rather than something that is FPGA specific. Because if it's FPGA specific, we would limit ourselves to FPGA people. We want to open ourselves up to people who are targeting CPUs, GPUs, other kinds of celebration devices as well. It has to abstract away some of the underlying details of the hardware. Verilog and VHDL design, traditional Verilog and VHDL design, are kind of like assembly language programming. They are very, very useful in certain situations, but we don't have to make that the mainstay of our design methodology. The price of our abstraction cannot be too high, however, because if we abstract so much but lose all of our efficiency, then the FPGA is pretty much a useless piece of silicon. And somehow we have to get to this point where we have software like compilation and debug cycles. We cannot have these 24-hour cycles where you're constantly looking for the flow every time you need to make a change. Now, a few years ago, we came upon OpenCL. OpenCL came into existence in mid-2008. And we found this was something that was quite interesting because it offered a solution to some of these problems. So while I'm going to talk about OpenCL today, I should note, it doesn't solve everything that I've talked about. It's not the solution to all problems, but it's one piece, I think. And we have to start as FPGA companies building these things in steps. Now, here's the big idea behind OpenCL. If you take a traditional C program shown on the left, you'll have some function, you'll have some loops. Here we have a very simple function that does vector multiplication. And the multiplication differentiates that loop. It's obvious that this loop can be parallelized. What OpenCL asks you to do is make that explicit. So instead of having the loop index, what we have is a thread index. So here we have IDs, get global ID. Get global ID is the index of many parallel threads, basically corresponding to if you were to run all the iterations of that for loop in parallel. So that's the work that you have to do in OpenCL. Nothing comes for free. OpenCL tells you that you can get acceleration if you make your loops that are parallelized and explicit. So that's what you have to do in terms of translating a normal C program into an OpenCL program. You have to identify which functions are hotspots, map them as kernels, and then say which of the loops can be parallelized and make that explicit. OpenCL's programming model at a very, very high level. It's somewhat like the picture shown on this slide. You have a pure software routine. It's running on a host processor, and you have a portion of your application that is a highly data parallel function. It is called the OpenCL kernel, and it runs on an accelerator device. And accelerators can be FPGAs, GPUs, DSP processors, even other CPUs as well. If we dive down a little bit more into the host program, you may have something like this. In your main routine, you're reading some data from a file, maybe you're manipulating the data, and you get to something where it's just very, very computationally complex, and you want to offload it onto an accelerator. And the way you do that in OpenCL is by copying the data from the host to the accelerator device, telling the accelerator device, I've sent you some data, please run your acceleration on the data I've just sent you, and copy the data back. And those are the 3 OpenCL API calls that allow you to do that. The OpenCL kernel itself, so this is the highly data parallel part of OpenCL. Here I show an example of an OpenCL kernel that's doing vector addition. So basically what we're trying to do is add up the vertical slices of these 2 arrays and come up with an answer. So what we're going to do here is to launch 8 parallel threads that are going to handle these 8 slices. So basically the first thread will have a thread ID of 0, and what we'll do is the answer of 0 is going to be equal to A of 0 plus B of 0. So every thread has an ID. That's how it knows which data to work on. So more generally, it knows which sub-portion of the problem to work on. And that's really the big idea behind OpenCL. It doesn't get a whole bunch more complex than this, although there are some extensions that allow you to do things that are a little bit more fancy. Now, when we take OpenCL applications and map them to Altera FPGAs, we're doing it in the following way. We have that big portion of your application, the host program, that's just pure software. And what's going to happen is we take that, we run it through a standard compiler. So it could be Visual Studio, GCC, whatever it may be. And what happens there is that the application links against a library that Altera provides. And that library implements the OpenCL API functions that allow you to communicate to the accelerator device over PCI Express in this particular case. So we've abstracted all of that implementation and all of that complexity through the use of standard software APIs that are defined by OpenCL. The OpenCL kernels go through our Altera OpenCL to FPGA compiler, we call it ACL. It produces a binary soft, so that's the programming file. It gets downloaded onto a standard board. So this is something that's key. We don't support every single kind of board that a person can imagine. We support a few very, very standard boards that are dedicated for acceleration. So here our OpenCL compiler knows everything about the board. It knows about memory interfaces. It knows about the PCI Express connection. And because of that, it can do a lot of very fancy optimizations behind the scenes for you. The board design itself all looks like this templated architecture that I show on this slide. So at the top, we have memory controllers and PHYs, several of them actually, because we want as much external memory bandwidth as we can get. We have a PCI Express interface that connects to the x86 processor, so we can basically stick this board into a system and have it act as a GPU replacement. The OpenCL kernels are compiled down into those green boxes, so there may be several kernels in any application. They may be replicated several times to get the required throughput and latency of the particular application. We look at a high level what it is we're trying to do with that vector addition example. We basically take the OpenCL kernel that says we're going to do a vector add of those two elements and produce a result. And here, all we're going to try to do is to convert it into a circuit at the high level that looks like the picture on this slide. Basically, we're doing two loads from memory. We're taking those results, adding them together, doing a store back to memory. We may replicate this structure many, many times, and we'll also instantiate the PCI Express and DDR logic for you as well. Now, the most important thing that you have to understand about mapping OpenCL to FPGAs is how we actually take these multi-threaded kernels and map them onto an FPGA. At first, when people hear about multi-threaded kernels, they think about GPU structures where you may have multiple processing elements, multiple processors, things of that nature. Now, that's actually very, very inefficient on an FPGA. That's not at all what you want to try to do. What we do on an FPGA is try to take advantage of something called pipeline parallelism. And it's best illustrated by example. So imagine that we had this vector addition circuit, and we would insert registers at the horizontal cut lines that I've shown there. And of course, the load units and the adder and the store units are all, in reality, pipeline many cycles as well. But let's assume they're all one-cycle operations just for simplicity. And what we'll have here is, imagine that we had the 8 parallel threads. So you have 8 thread IDs in some kind of queue. On the first clock cycle, we clock in thread ID 0 into the registers at the top. And what this means is that the two load units will fetch the data in the A array and the B array for thread ID 0. The next clock cycle, that data is returned, stored in the output registers, and at the same time, we're fetching data for thread ID 1. Next clock cycle, the data for thread ID 0 has been added together. We're fetching the data for thread ID 2. So you can kind of see how this works. On any particular clock cycle, there's several threads in the pipeline, and each part of the pipeline is processing the different threads context. So that's why I wanted to show before, when you were thinking about the Burr filter and how it's actually a multi-threaded circuit, OpenCL really generalizes this concept with multi-threading, and it is actually equivalent to pipeline parallelism. So I want to dive in a little bit more detail about Altera's OpenCL system architecture, and then I'll show a few examples as well. So this is the picture I showed before. We have two big parts of the OpenCL system. So all of that stuff highlighted in the dotted box is our external interface. Now, at a high level, it looks like the picture that we showed here. What we have is a PCI Express connection to multiple DDR interfaces, actually, with DME cores in the middle. This is one of the key parts in any OpenCL system. We want extremely efficient communication between PCI Express and DDR. This is generally a very, very difficult thing to design. So we've built this in such a way that you don't have to worry about it. We've designed this for you. We have shipped it with known boards, so it is placed, routed, and locked down. It is guaranteed to meet timing. You never have to worry about a timing failure in this particular domain of the external interface. It also has a very, very efficient interconnect structure that allows the kernels to have access to DDR memory as well. The other big portion of the OpenCL system is the thing that we auto-generate from your kernel descriptions. So this is known as the kernel system, and it also has somewhat of a template structure as well. So there are things that we know that are very, very similar in each kernel. OpenCL describes the way in which threads are iterated over in terms of an n-dimensional space. But the the most interesting things are the things in this green box, so the kernel pipelines. And that's where we take your kernel description written in OpenCL and create these pipeline functional units that are connected together to actually implement your algorithm. And to do that, we have a CAD flow that is based upon Clang and LLVM. Clang is an open source parser developed by Apple Corporation. And we have extended it to understand all of the OpenCL standards. OpenCL is actually has a lot of extensions on top of straight C, but we've added all of these. It produces an intermediate representation, so this is kind of like a high-level assembly language view of your program in LLVM format. LLVM is an open source compiler project. Most people in this world of compiling high-level languages to hardware, all are based on LLVM. It is a very good framework for doing that. We go into optimization passes from this intermediate representation. So we have about 150 different optimization passes that try to restructure your code in such a way that it's good for the final FPGA implementation. So these would be things like vectorizing your kernel, removing branches, fusing together loops, all of the things that make a kernel look like if it was a feedforward pipeline, look like it was the wonderful fur filter example that I showed earlier. The last step is to take that intermediate representation, finally generate Verilog from it. Here we do a lot of the things that you traditionally know as high-level synthesis, so scheduling, resource sharing, things of that nature. So for this, I'd like to go into a couple of case studies. And I just looked at two benchmarks here. One is an information filtering benchmark, and it's described in detail in a paper that's attached in the proceedings. So maybe you can look at that at any time. The reason that I chose this one is that there's been previous published work on this particular benchmark, and it's been published at FPL a couple of years ago. And there's a good AND implementation that we can compare against. It's also very, very high on external memory bandwidth, low on compute. So it's exactly the opposite kind of thing that you would think FPGAs would be good at. The next application that we'll look at is Monte-Carlo Black-Scholes. So it's a financial benchmark to compute option derivative prices. And it's very, very heavy on compute and almost negligible on bandwidth. So both ends of the spectrum. Let's see what we can get. So first thing I'll do is start off with the information filtering benchmark. So this is a very, very simplified version of generalized information filtering. And what we're trying to do here is assume that we have multiple sources of documents coming into a system, they're going into some kind of database. And what we're trying to do here is score the documents against some relevance criteria against search profiles. So these search profiles may be dedicated to particular users of the system. So examples of this is if you have news feeds that are coming in and you have a particular interest in some kinds of articles. Once these feeds come in, it gets filtered against your interest, and then the article will get emailed to you. Or in our world, you have all these conference and journal publications, and you want to know if there's a new publication that matches your research interest, gets emailed to you. So things like that. And the general idea here is that documents are converted into a bag of words format. So a bag of words format means that you have a term ID. So basically an ID into a dictionary that represents which word you're talking about. So this is generally about 24 bits. That allows you to represent about 16 million different words. And generally that's good enough for the English language at least. So it's a term with a frequency, so the frequency of occurrence in the document. The search profiles are represented by a term and a weight. And this weight is a 64-bit fixed point representation. So generally what you're doing is you're scanning through a document, looking at all the terms, and going off to an external array to see inside the search profile, does that term have a weight? Generally, in most realistic scenarios, most terms will have no weight once you look it up in the search profile because a person's not looking for everything. They're trying to filter down to some specific set of documents. So most accesses will actually return 0. The equation that we use here to store a document, very, very simple summation. It's basically the frequency times the weight of the term. If you take that simple equation, express it as OpenCL, you can do it very, very, very directly. It's just a loop that sums up the frequency times the weights over a particular, over all of the terms in a document. Now, to get the parallelism, what we've done is say we're going to process multiple documents in parallel. So this is simple initial cut of an OpenCL implementation, handling multiple documents in parallel. It's a fine OpenCL implementation. But what we want to do is generalize this code so that it works easier to different styles of architectures. FPGAs and GPUs benefit from something called memory coalescing in the OpenCL world. This is the optimization where if you have consecutive threads, what you want them to do is access consecutive memory locations as much as possible. Now, if you look at the simple implementation that I just showed, we have a thread that's accessing the first term of the first document. The next thread is accessing the first term of the next document. And those can be quite far apart in memory. You're not going to take advantage of this memory coalescing operation. So we can actually restructure this OpenCL code in a little bit more complex manner so that we have groups of threads, maybe processing 64 consecutive elements in a particular document, and then they'll move on to the next 64 elements. So in using this kind of technique, we have consecutive groups of threads accessing consecutive elements. So the amount of threads that we divide a document into is denoted by T. Now, the reason that this is important is that if you look at how FPGAs access external memory, it's usually by something like DDR2 or DDR3. And these memories are clocked at very high frequencies on both edges of the clocks, either 400 or 800 megahertz. And to make that reasonable when it comes into the FPGA core, you're getting in data about 256 bits at 200 megahertz or 512 bits at 200 megahertz, something like that, very, very wide at a lower clock frequency. Now, if you have an algorithm where you want to access a single integer, let's say a 32-bit integer, you basically have to say, I need a 256-bit chunk, because that's the interface that's available to you on the FPGA. And if you're only going to use 32 bits out of that 256 bits, you've just lost 7/8 of your bandwidth right there. So you have to make requests in a more intelligent fashion. So if you remember, the OpenCL implementation of FPGA is all about pipelining, and we're getting threads in on every clock cycle. Now, if these consecutive threads are accessing consecutive memory locations, what we can do in these load store units is basically buffer up the threads, look at their sequence of addresses, and when the sequence of addresses is a very large group, we can make one large burst request to DDR memory. And when that data all comes back, we can just feed off pieces of that data back into the pipeline. This style of communication with external memory is extremely efficient, and it's your only chance of using DDR efficiently. I said also before that most of the accesses to external memory are going to return you 0 for the profile weights, the search weights, basically. Now, one of the things that we can do to get around that is let's not access external memory needlessly. We can use a Bloom filter in the application. The Bloom filter is an extension of the hash table where you have multiple hash functions into the same data structure. And basically, when the user is constructing their search profile, now there are just a few entries that are going to be 1. And we set those hash bits to 1. And anytime that we're looking for a particular term in the document, we check the hash table before going out to external memory. And the key here is the hash table is much, much smaller than the size of the external memory buffer. So we can keep it on chip. We took this OpenCL implementation and we ran it on 3 different platforms. So multi-core CPU, so an Intel Xeon W3690 with a Tesla GPU, C2075, and a Altera Strix 4 530 FPGA. We did this so that we could keep the comparisons relatively constant in terms of things having around the same process. We couldn't quite do that for the CPU because we didn't have one available. The interesting thing to note here is the external memory bandwidth that's available on the CPU and GPU especially, in comparison to the very, very small amount of external memory bandwidth available on the particular board that we used the Jurassic D for. Now, when we took this OpenCL code and ran it on the CPU, it's important to note that when people have traditionally done comparisons to CPUs, and they're FPGA designers, they may spend months or even a year doing their FPGA design, doing all kinds of optimizations to it. And when they compare to a CPU baseline, they do GCC-03 subsequential program.c. And that's their comparison. And that's not fair. We're kidding ourselves if we do that. OpenCL really allows us to do better than that in some senses, because if you look at the latest version of the Intel OpenCL SDK, it's able to take advantage of the SSC vector instructions, for example, that Intel CPUs have. It's able to take advantage of the multiple cores. So all of these things, all the kinds of parallelism that the CPU gives you, you can take advantage of using OpenCL. Now, if we look at the results that we got here on the CPU, basically in the middle column here, I'm looking at millions of terms processed per second. And on the final column, it's millions of terms per joule. So that's the performance per watt. It becomes operations per joule when you work out the math. On the CPU, the best implementation was actually not dividing the document at all, basically using one thread per document. And that kind of makes sense because each document basically gets loaded into one of the individual core caches. And we're able to achieve a result of about 2 billion terms per second for the CPU and about 15.9 million terms per joule. And doing this, we have to do lots and lots of different parameter sweeps and optimizations to make sure that we got the best possible implementation on the CPU. Looking at it on a GPU, there are other kinds of optimizations that you have to take into account. GPUs have a hierarchical memory structure. They have different styles of memory. It's a constant memory used for the bloom filter, for example, local memory, which is a scratch pad space, and of course the global off-chip DDR memory. Here we did many, many different optimizations, looked at different ways of structuring the code so that it would be good for the GPU. We came up with a solution that said GPU at best can get about 3 billion terms per second, and energy efficiency of about 15 million terms per joule. On the FPGA, very, very similar in terms of the other two platforms. Just kind of like to show how the data is organized. This particular FPGA board has two DDR2 800 memory DIMMs. So that's the memory clock running at 400 megahertz. And the data is kind of striped across these two memory DIMMs so we can use them in parallel and get as much bandwidth as we can from having these two DIMMs. One of the key innovations that we have in Altera's OpenCL compiler is the ability to create a soft read-only cache for constant data. So there's some details in the paper if you want to read about it. We can use tricks where we double pump the on-chip RAMs to help us to make this caching structure efficient. And that really allows us to bring the bloom filter in from external memory, put it onto an on-chip cache, and make sure we have really high bandwidth to it so that we can ensure that we don't have to access external memory needlessly. Here, for the FPGA implementation, basically dividing the document into about 64 threads seemed to be the best possible implementation. We're getting about 1.7 billion terms per second that's being able to be processed. So this is lower than the CPU and GPU. But however, one of the interesting things that we note here is that we can process about 83 million terms per joule. So the energy efficiency is quite good. If we were to take this board and just add 2 more DDR2 banks to it, we could get to almost equivalent performance to what the GPU was able to do. And that's actually something that's very, very interesting Because if you look at the cost of power, it's actually quite significant in this whole data center world, kind of tying back to where I started. If you're using about 200 watts less but getting about the same performance, that's about $300 per year. And that becomes a significant factor when you start looking at the total cost of ownership. So that's the biggest constraint in terms of getting more and more compute into data centers. So this cost is almost irrelevant, because if they wanted to get more compute, they're so constrained they would have to build another data center. So it is somewhat simplistic and somewhat of an underestimate in some senses. The next example I'd like to look at is Monte Carlo Black-Scholes. So this is a simplistic benchmark. It's used for evaluating stock option prices. Basically, you take a stock and you simulate the path of the stock price over time, and you get to some endpoint, and you want to figure out what is the expected value of the stock option. And NVIDIA does very, very well in this particular domain. Now, this is a slide I took from their website, where you can see that they went into a bank and are doing similar computations to this. And they were basically able to take 500 CPU servers and replace it with 2 of their Tesla GPU boxes. So one of the things I said earlier was that they seem to do really well in this world of high-performance computation, although they're using extreme amounts of power. And the reason that they can get away with that is that they're able to reduce the amount of compute by so much, it doesn't really matter what their power is in this particular example. And if you look at this example, it's about 300 lines of OpenCL code. It's split into about 4 different parts. We have a machine twister, uniform random number generator, goes into an ICDF function, which converts the uniform distribution into something that's more normal. We can use that to compute the motion of the stock prices. And the final stage is basically a parallel reduction at the end that's used to compute the payoff. If you look at the innermost loop of this particular algorithm, you'll see that there are lots of logs and square roots. GPUs are traditionally very, very good at things like floating point additions and multiplies. They have many functional units that are dedicated to that. However, anytime you have to use more complex functions like square roots and logarithms, they have far fewer units that are dedicated to that kind of computation. So they may not get their market and speed up on these types of applications. Also, you'll notice that there's a lot of branching here. There's a lot of if statements and things like that. And GPUs are simply machines. Everything has to run in lockstep on a particular stream multiprocessor. So when you have a bunch of parallel threads and they have to go through different paths, you basically have to serialize these parallel threads. So some threads go through path A, they wait, and the next set of threads go through path B. So you lose some of your parallel speed up because of this branching. So bottom line is that if you were to look at the results that we're comparing on the C2575 Tesla GPU and the DD4 card. So again, we went through many optimizations on both platforms and tried to get the best possible result. We're saying that we can pretty much match the GPU in terms of its performance. However, we're using 10x less power to do that. And this is something that's very, very compelling in this world, at least, because a lot of financial companies are trying to do these kinds of applications. And as you can imagine, a lot of them are located in New York, close to the stock exchange. Just getting power into these data centers is extremely prohibitive, and they will pay almost anything to get more compute, but they just cannot build more data centers to do this. So anything that reduces their power is something that's very, very interesting to them. So I'd like to conclude by just talking about some research and recommendations in this world. And I think if you look at FPGAs, they do have somewhat of a bright future in this world of computation. I mean, we do have to do some research to get us there. I mean, we have to look at standard programming models and tool usability to make this widely available to the world of software programmers. Now, when I talk about software programmers, it's not just a regular programmer. You don't find as many regular programmers as people that can do OpenCL. So OpenCL is something that's more complex than just regular sequential coding, and if we can even open it up to the guys that are doing the regular sequential coding, it will allow us to even target more of that market. We need to target boards that are meant for compute acceleration. A lot of the boards that we have out there for FPGAs, they're standalone boards. They have a lot of different things on them. But if you look at some of the success that NVIDIA has had in this domain, you can basically take a board, you can plug it into your system, you can do immediate compute acceleration. So that's something that's wonderful, and that is something that I hope that we can make available in the FPGA world as well. And to do that, it's not just about the hardware. We have to have the entire software stack ready to support that. So that means high-level languages, and OpenCL is just one example of that. And along with the languages, we need to have debugging and profiling and libraries as well. One of the good things about these guys in the GPU worlds is that they have all kinds of libraries that are great for linear algebra and FFTs and things of that nature. And finally, I mean, when we as FPGA people look at applications and try to figure out how we're doing on these applications, I encourage people to look at GPUs and don't underestimate the power of the GPU in these multi-core architectures, and let's do fair comparisons of ourselves versus them. You can see all kinds of different studies out there about how GPUs can even start to infiltrate the traditional server market. So I've talked a lot about high-performance computing, but even things where people are doing database queries and things like that, or more of the traditional kinds of servers, GPUs are finding their ways in there as well. And I would find it kind of sad if GPUs took foothold in these domains, because FPGAs are really ideally suited for doing these kinds of things. We just need to give people the ability to program them better. When you're thinking about architectures and FPGAs and programming models, it's also important to think about what does the ideal FPGA look like going forward. A lot of the things that we have to do in this Altera OpenCL to FPGA compiler are really quite complex and incredibly difficult CAD problems, because the architecture is not perfectly suited to do this kind of OpenCL conversion. Now, what things can we do architecturally to allow high-level languages to be compiled to FPGAs more efficiently? I think that's something that would be interesting to research. And then let's look at the language models themselves and what drawbacks do they have. If you look at OpenCL today, one of its big drawbacks is that it's very host-centric. All of the operations basically get centralized through the host processor. The host processor is doing all the scheduling of the accelerator. Now, that's something that's perfectly fine if you have a very, very powerful host processor. But in the FPGA world, many of our applications, and the picture on this slide, what we really want to have happen is that the host processor sets up the computation, sets up the communication between kernels, and just says go. And once that happens, we're able to take in packets, or take in streaming data directly from I/O, go through the kernels, and then send out data back through the I/Os. And that's something where I think FPGAs really shine and can do very, very well at, and something that the language model needs to evolve to allow to support this. So before I wrap up, I want to say that what I've talked about here today is a lot of new ways to use FPGAs and different application domains. So Altera supports a lot of innovation in these spaces. We want to see what you guys can come up with as well. So we have this Innovate Europe contest, and we're looking for impressive ways to use FPGAs, innovative application domains. So if you want more information, please just go out and see us at the university program booth, and they can tell you all about it. And before I wrap up, I just want to give you some demos of Altera OpenCL in action. Unfortunately, this time I didn't bring a board with me, but I can show you some video captures of things that we've done at Altera's Technology Center. So this is actually a video capture of an Intel demo. It's called an Intel shallow water demo. So it's actually a complete game-like simulation of this boat running in a lake. And this is written completely in OpenCL in a C++ application on the Intel host processor. This application is incredibly complex, as you might imagine, and it's something that we could just take from Intel, compile it to Altera's OpenCL compiler, download it onto D4 board here, and have it run. So that's something that's quite amazing, because doing an application that complex in HDL would just be almost infeasible. There are many, many other applications as well, so I have a particle simulation demo as well. So this is a particle simulation demo that we took from NVIDIA, and again, we're able to take that OpenCL code that they use on NVIDIA GPUs, because that's their biggest constraint in terms of getting more and more compute into data centers. So this cost is almost irrelevant, because if they wanted to get more compute, they are so constrained, they would have to build another data center. So it is somewhat simplistic and somewhat of an underestimate in some senses. The next example I'd like to look at is Monte Carlo Black-Scholes. So this is a simplistic benchmark. It's used for evaluating stock option prices. Basically, you take a stock and you simulate the path of the stock price over time, and you get to some endpoint, and you want to figure out what is the expected value of this stock option. And NVIDIA does very, very well in this particular domain. This is a slide from their website where you can see that they went into a bank and are doing similar computations to this. And they were basically able to take 500 CPU servers and replace it with 2 of their Tesla GPU boxes. So one of the things I said earlier was that they seem to do really well in this world of high-performance computation, although they're using extreme amounts of power. And the reason that they can get away with that is that they're able to reduce the amount of compute by so much, it doesn't really matter what their power is in this particular example. And if you look at this example, it's about 300 lines of OpenCL code. It's split into about 4 different parts. We have a machine twister, uniform random number generator, goes into an ICDF function, which converts the uniform distribution into something that's more normal. We can use that to compute the motion of the stock prices. And the final stage is basically a parallel reduction at the end that's used to compute the payoff. If you look at the innermost loop of this particular algorithm, you'll see that there are lots of logs and square roots. GPUs are traditionally very, very good at things like floating point additions and multiplies. They have many functional units that are dedicated to that. However, anytime you have to use more complex functions like square roots and logarithms, they have far fewer units that are dedicated to that kind of computation. So they may not get their marketed speed up on these types of applications. Also, you'll notice that there's a lot of branching here. There's a lot of if statements and things like that. And GPUs are simply machines. Everything has to run in lockstep on a particular stream multiprocessor. So when you have a bunch of parallel threads and they have to go through different paths, you basically have to serialize these parallel threads. So some threads go through path A, they wait, and the next set of threads go through path B. So you'll lose some of your parallel speed up because of this branching. So bottom line is that if you were to look at the results that we're appearing on the C2575 Tesla GPU and the DD4 card. So again, we went through many optimizations on both platforms and tried to get the best possible result. We're saying that we can pretty much match the GPU in terms of its performance. However, we're using 10x less power to do that. And this is something that's very, very compelling in this world, at least, because a lot of financial companies are trying to do these kinds of applications. And as you can imagine, a lot of them are located in New York, close to the stock exchange. Just getting power into these data centers is extremely prohibitive. And they will pay almost anything to get more compute, but they just cannot build more data centers to do this. So anything that reduces their power is something that's very, very interesting to them. So I'd like to conclude by just talking about some research and recommendations in this world. And I think if you look at FPGAs, they do have somewhat of a bright future in this world of computation. I mean, we do have to do some research to get us there. I mean, we have to look at standard programming models and tool usability to make this widely available to the world of software programmers. Now, when I talk about software programmers, it's not just a regular programmer. You don't find as many regular programmers as people that can do OpenCL. So OpenCL is something that's more complex than just regular sequential coding. And if we can even open it up to the guys that are doing the regular sequential coding, it will allow us to even target more of that market. We need to target boards that are meant for compute acceleration. A lot of the boards that we have out there for FPGAs, they're standalone boards. They have a lot of different things on them. But if you look at some of the success that NVIDIA has had in this domain, you can basically take a board, you can plug it into your system, you can do immediate compute acceleration. So that's something that's wonderful in there. It's something that I hope that we can make available in the FPGA world as well. And to do that, it's not just about the hardware. We have to have the entire software stack ready to support that. So that means high-level languages, and OpenCL is just one example of that. And along with the languages, we need to have debugging and profiling and libraries of ML. One of the good things about these guys in the GPU worlds is that they have all kinds of libraries that are great for linear algebra and FFTs and things of that nature. And finally, I mean, when we as FPGA people look at applications and try to figure out how we're doing on these applications, I encourage people to look at GPUs and don't underestimate the power of the GPU in these multi-core architectures, and let's do fair comparisons of ourselves versus them. You can see all kinds of different studies out there about how GPUs can even start to infiltrate the traditional server market. So I've talked a lot about high-performance computing, but even things where people are doing database queries and things like that, or more of the traditional kinds of servers, GPUs are finding their good ways in there as well. And I would find it kind of sad if GPUs took foothold in these domains, because FPGAs are really ideally suited for doing these kinds of things. We just need to give people the ability to program them better. When you're thinking about architectures and FPGAs and programming models, it's also important to think about what does the ideal FPGA look like going forward. A lot of the things that we have to do in this Altera OpenCL to FPGA compiler are really quite complex and incredibly difficult CAD problems, because the architecture is not perfectly suited to do this kind of OpenCL conversion. Now, what things can we do architecturally to allow high-level languages to be compiled to FPGAs more efficiently? I think that's something that would be interesting to research. And then let's look at the language models themselves and what drawbacks do they have. If you look at OpenCL today, one of its big drawbacks is that it's very host-centric. All of the operations basically get centralized through the host processor. The host processor is doing all the scheduling of the accelerator. Now, that's something that's perfectly fine if you have a very, very powerful host processor. But in the FPGA world, many of our applications, and the bigger picture on this slide, what we really want to have happen is that the host processor sets up the computation, sets up the communication between kernels, and just says go. And once that happens, we're able to take in packets, or take in streaming data directly from I/O, go through the kernels, and then send out data back through the I/Os. And that's something where I think FPGAs really shine and do very, very well at, and something that the language model needs to evolve to allow to support this. So before I wrap up, I want to say that what I've talked about here today is a lot of new ways to use FPGAs and different application domains. So Altera supports a lot of innovation in these spaces. We want to see what you guys can come up with as well. So we have this Innovate Europe contest, and we're looking for impressive ways to use FPGAs, innovative application domains. So if you want more information, please just go out and see us at the university program booth, and they can tell you all about it. And before I wrap up, I just want to give you some demos of Altera OpenCL in action. Unfortunately, this time I didn't bring a board with me, but I can show you some video captures of things that we've done at Altera's Technology Center. So this is actually a video capture of an Intel demo. It's called an Intel shallow water demo. So it's actually a complete game-like simulation of this boat running in a lake. And this was written completely in OpenCL in a C++ application on the Intel host processor. This application is incredibly complex, as you might imagine, and it's something that we could just take from Intel, compile it to Altera's OpenCL compiler, download it onto D4 board here, and have it run. So that's something that's quite amazing, because doing an application that complex in HDL would just be almost infeasible. There are many other applications as well, so I have a particle simulation demo as well. So this is a particle simulation demo that we took from NVIDIA, and again, we're able to take that OpenCL code that they use on the NVIDIA GPUs, compile it through Altera's OpenCL FPGA compiler with no changes at all. We're able to get something that immediately runs, and we can evaluate its speedups. We can change it and change the parameters in ways that allow it to be a little bit more optimized for FPGAs. But again, just getting that first working implementation is something that's tremendously difficult and complex in the FPGA world, and something that I think our tool really addresses and helps you to do. So with that, I think I'll conclude and leave some time for you guys to ask any questions that you might have.
I'm curious, how does OpenACL handle a stream model like you had on slide 89, where you have multiple parts of an application, and especially we like to take hardware people, or semi-hardware people like to take advantage of priority queues, things that are much more efficiently done in hardware. Do those need macro blocks, or are those structures, or do they translate immediately, or how does that work in OpenCL?
Summarize the question.
Okay, so I believe that he was asking about the streaming model of how it relates to that last slide that I showed there, and some of these things in the streaming model are more efficiently represented as hardware blocks, and how do we work on incorporating that within the OpenCL framework. So let me say this. What we are shipping is a product that supports OpenCL. Right? So you can take OpenCL as it's written and compile it down to Altera FPGAs. OpenCL itself supports limited forms of streaming. Right? Everything has to be basically dumped to some kind of memory buffer, but you can't have everything completely concurrent if you want it. Now, the interesting thing there is, how do you take OpenCL and then interface it with hardware blocks that are more efficient for specific types of applications? And that is something that we are now beginning to ship with our product and explore. So there is a way to do this. We have APIs that allow you to basically put in blocks into the system and basically have software wrappers for them.
One more quick question.
I have a question.
Yeah. So, exponential back off there.
So OpenCL is fairly new and it's changing very rapidly. So I assume that you're supporting version 1.2, is that correct?
That is correct. So
Do you have plans? Like, what happens when new versions come out?
OpenCL doesn't change that rapidly. One of the things about OpenCL is it's actually frustratingly slow in terms of how the language model changes. And the language doesn't change all that much from release to release. You basically get a few new additions and features, and we will definitely be able to keep up with that pace. One of the things that we are trying to do is actually drive OpenCL to be a little bit more friendly to FPGAs. So we are actively working to make the language a little bit better for these kinds of streaming applications.
So my understanding is that the version that's going to come out next is actually quite different. It's going to be C++ based. The way you describe things is going to be very different.
No, that's not true.
Another very quick question for Coffee.
In the processor world, what happened is that the processor companies acquired GPU technology. So they come up with something combined to exploit both worlds. Do you see something similar happening to the FPGA world?
Yeah, so look at the FPGA world today. I mean, both companies have announced products with ARM processors, and where is that eventually going to lead? It's very interesting, right? I mean, what is an FPGA eventually going to become? It's going to become a lot of processors with some programmable logic around it. Will it become something that has different kinds of maybe finer grain processors? It's hard to say, but it's definitely something that I think both companies are exploring in the evolution of the FPGA.
I'm going to wrap up there. Thank you very much for a fascinating talk. We've got a nice gift for you. It's a very mathematically inspired sculpture. And thanks for